Hey, good to see you. This is the summary and the notes from September 15th, Tuesday from Accelerated 9, in case you were absent or your Zoom went out or you just kind of wanted to see it again. Real high tech here, my Sharpie and my scrap paper. Here's a few things that we did. We went over the answers to page 5 and 6, and you could find those on Google Classroom. It's under classwork materials. And there's something called 1.2 task slides for teams. And that's where we did that work, and your team members put the answers up for you. But we are going to do a little bit of notes on page 6 in just a second. You have homework that's due tomorrow, Wednesday. It's posted with a video. It's under the assignments on weeks 3, 4 in Classroom. Make sure to read what I wrote and watch that video before you do the homework. It's only a few minutes long. And what we're going to do today, we're going to do a little bit of just a little bit of check-in on page 6. And then we're going to go over 2 other problems that we did today. Okay, so let's talk about page 6 first. So if you did a table of values for that problem on page 6, then what you noticed was that you got in the first one, there were 7, and then this one, I think there were 28, then 63, and then when you drew the fourth figure, there were 112. So then when you did the first differences, you found out it was plus 21, plus 35, plus 49. Now, if you haven't done the second differences yet, that's totally fine, but why don't you pause, go ahead and do the second differences, and then press play again. You're back. Here we go. So the second difference is plus 14, right? So what that tells us is because the second differences are all equal, so if the, that one's not going to work. Use green. So if the first differences are always changing, and the second differences are always the same, second differences are what we call constant or the same, then you know that you have a quadratic function. And last time in class, we talked about how a quadratic function is going to have an x squared in it, and that it's based on, whoops, you can't see that, and that it's based on quadrilaterals. So our first difference was always changing. Our second difference was plus 14. And I'm assuming that you did okay with the graphing. I'm not going to necessarily go over that. So then we wanted to find the explicit equation. Let me unzoom this a little. There we go. So we wanted to find the explicit equation, and sorry, I'm having all sorts of trouble here. There we go. And I gave everybody a hint. We didn't do a lot about writing equations today, but a hint I gave everybody was that when you write an explicit equation for a quadratic, it's just for quadratics, then you're going to have f of x equals, and your leading number or leading coefficient, as it's called, I also sometimes call it like a multiplier. The number that's going to come first, that's going to multiply, is always 1/2 of your second difference. I should write that with an S. 1/2 of your second difference. So that means just by looking at this, we can get a clue about that explicit equation. And if I look at my second difference was 14, 1/2 of my second difference is 7. So there should be something about a 7 that's going to help us here. And you might already be able to see it. Because I already said, if you were here the day before, I said, hey, this problem is going to have to do with squares and it's going to have to do with x squared. So if you think about squares and x squared, can you see that, x squared? Well, then I'm like, wait, how does that help me? Because like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Like, how does that help? But then you discover the 7. And you're like, oh, wait. 2 squared, which is 4, times 7 is 28. 1 squared times 7 is 7. 3 squared times 7 is 63. See how there's a times 7 every time? And 4 squared, though you may not know this off your head, 4 squared, that's not a 42, that's a 4 squared, times 7 equals 112. So I was right. It has to do with squares, and it has to do with x squared, and then 1/2 second difference. So actually, this equation ended up being 7 times x squared, where x is the term number. Now, I told the class I'm kind of an equations person, so I look for the patterns in the numbers. But a lot of people find the patterns much more easily visually. So I've already drawn all over these. But if you look at this one, if you look at, you have, 28 little squares, right? But this drawing is actually made with 7 other squares. Right? And I guess since I already did this in both the classes, I can outline them. 1, 2, 3, 4, 5, 6, 7. So it's 7 squares. And you know how this is size 2? Well, each square is a 2 by 2 square. Get it? So there are 7 2 squares. This one also ended up being 7. They all ended up being 7. This one ended up being 7 squares. And so what we were doing is we had 7 of these squares, and these were like 3 squares. Get it? 3 by 3. So 7 times 3 squared. 7 times 2 squared. So the 3 matches up with the size or the term, and the 2 matches up with the term. Remember, that's our x. So that means I can put an x in place of the 2, and I get 7x squared. I can put an x in place of the 3, 7x squared. And that even works for the 4. So that's one way that we can develop that equation. And you might be thinking, oh man, I would have never thought of that. Totally fine. You might think of it next time, though. And that's the idea. Sometimes once you see something once, next time you see something similar, you're like, oh yeah, that makes sense. So then what we did is I said, hey, let's stick with this idea. Let's look at some other kind of quadratic problems that have to do with this. So I ask everyone to draw this one and call it example 1 in their notes. And you can go ahead and draw it now. I'll put in a few things in case you can't see very well. This is a 3 by 3. This is a 4 by 4. And this is a 5 by 5. So go ahead and draw that. I hit pause, draw that. You're back. So you have it all drawn. Very good. First thing we're going to do is make an XY table. And it's good to remember that the X is the term number. Term number. And the Y is the total squares. It's the area. Right? So if I count this one, I get 9. So when we're on term 1, that's a 1, really, I promise. When we're on term 1, we have 9 squares. You can tell me term 2, term 3, and go ahead and draw term 4, okay? You should be able to figure out maybe what term 4 is. So draw that also. So I'd like you to hit pause, fill this in. also fill in the first and second differences and draw term 4. And I'll see you when you come back in a second. So hit pause. So you probably got that term 2 is 16. Term 3 is 25. Oh my gosh, 25. And probably got that term 4 is 36. Maybe you didn't. That's okay. I'm sure you got these. So I'm like, hey, that's 3 squared, because I'm thinking about squares, right? 3 squared, 4 squared, 5 squared. So I could make a little guess that this was 6 squared. So what's interesting, though, is like, how am I going to, so I'm just going to draw this one. It's probably a 6 by 6, right? 1, 2, 3, 4, 5, 6 by 6. There we go. Oh, you can't see that. It's behind my head. There you go. It's a 6 by 6. So now this is kind of a weird situation. Like for term 1, I have 3 squared, right? For term 2, I have 4 squared. For term 3, I have 5 squared. And for term 6, I have 6 squared, right? 9, 16, 25, 36. But the thing is, we have to write an equation where you can input the term and the output will give me 9, 16, 25. So we're going to need like an f of x where x is the term number and the answer is these. So let's do our first and second differences. You already did that, right? Plus 7, plus 9. This is probably plus 11. Yep. Then our second differences are plus 2. So we know it's a quadratic. And then remember how I said that you're going to use 1/2 of the second difference. 1/2 times 2. 1. Great. Boring. But what that tells us is there's not going to be a multiplier. Oh, and that makes sense. Because, the other picture, every picture here was constructed from 7 squares. The pictures here are just constructed from 1 square. So that makes sense that we don't really have a multiplier. That ought to make our life easier, because since we don't have a multiplier, that means any manipulation that we do to x is going to be like adding or subtracting. So every square and rectangle problem, actually every quadratic problem, is really based on rectangles or squares. Remember we said that quadratics comes from the word quadrilateral? Because you think it means 4, but we have x squared, right? But where that comes from is that it's either based on squares or rectangles. Not like parallelograms or rhombuses, but it is based on squares and rectangles. So what that means is when we have a quadratic, we can often think of it as the area of a square or the area of a rectangle, which means we're going to use that like area equals base times height formula for a rectangle, or length times width, same deal. Or with a square, you might have learned it's side times side or side squared for a square. Those are all the same formula, right? Base times height, length times width, side times side. It's all the same. And you might want to pause and catch up with that just a little bit. But like, I'm assuming that you kind of are comfortable with the area of squares and rectangles. And then let's go back to our problem. Am I on the right one? Yes. So we're here and we want to base this on the squares. So what that means is if I want to basically have this be like length times width or base times height or side times side, I need to get an equation for the sides. So what I want to think is if x is 1, how do I turn a 1 into a 3? It's got to be the same way that I could turn a 2 into a 4. How can I term 3? How can I turn that into a 5? Like if x is 3, what would I have to do to x to make it 5? If x is 4, what would I have to do to x to make it 6? And it has to be the same thing for all of them. By the way, I usually ignore the 2's because like 2 times 2 is 4, 2 plus 2 is 4, 2 squared is 4. I'd look at the other ones. So yeah, here I could do like 1 plus 2, right? Or x plus 2. 1 plus 2 is 3. Does that work here? Yeah. 2 plus 2 is 4. Does that work here? Yeah. X plus 2, 3 plus 2 is 5. Does it work here? Yes. 4 plus 2 is 6. And then the top is the same, right? Because it's the same number. So that means that our equation, that's a 1, but you don't even have to write it. X plus 2 for the side, x plus 2 for the other side. And really how we'd write that is f of x equals x plus 2, x plus 2. We're not going to distribute yet, by the way. And look, this works for each of them. X plus 2, oh, wait, here's a better one. X plus 2 is 5 times x plus 2 is 5. Another way people would write this is x plus 2 quantity squared. And then let's test it. Let's see if it works for f of 4. Is f of 4 4 plus 2 times 4 plus 2? Is it 6 times 6? Yeah, it really is. 6 times 6. It's 36. Boom. So the process was we made the XY table. We found the second difference just to find out if we had a multiplier. We took a look at how the numbers worked. And then we realized since there wasn't going to be a multiplier, that the only option is going to be to add or subtract something to x. And that we could write each side by saying it's the term plus 2 for the side. The term plus 2. That's kind of a different way to do patterns, right? It's just not as simple as looking at the previous number and doing something easy. So let's look at one more example. So copy this one down. I'll put some numbers on here so it's easier to see. 2, 4, 3, 5. It's a 3. So copy that one down. And then make the XY table and find the first and second differences. And draw term 4. And when you have that done, come back and see me. So hit pause. Come on, hit pause. Don't just wait for me to do it. Hit pause. You're back. And you figured all this out, right? So you would be like, hey, it's 1, 3. It's 2, 8. And you could either count 1, 2, 3, 4, 5, 6, 7, 8. Or you'd be like, oh, duh, 2 times 4 is 8, right? Right? Length times width, base times height. 3 times 5 is 15. And, I could figure out 4 a bunch of ways. But you know what I did? I was like 1, 2, 3. So I bet this one's going to be 4. And then 3, 4, 5. This one's going to be 6. 1, 2, 3, 4, 5, 6. Yeah, that works. So what is that? Whoops. That's a 4 by 6. Okay. Oh, so now I know. That's 4, 24. And you got your first differences. That's plus 5. That's plus 7. That's plus 9. And you got your second differences, plus 2, plus 2. Great. So we already know for our explicit, f of x equals, 1/2 of the second difference is 1/2 times 2. And that equals 1. So there's no multiplying. There's not a multiplier. So that means that I have to do like the base times height or the length times the width, however you want to do it. Actually, I usually do height times base. But however you want to do it, I'm going to have to do that kind of just adding or subtracting to x. So what I want to look at is how does my term number relate to the length of the sides? Again, I usually don't look at the 2's because there's just 2 is like too easy, right? 2 times 2, 2 plus 2, forget it. But if I look at the 1 and the 3, oh, well, here's a pattern I see right away. Look, it's term 1 and this side is 1. Term 2, this side is 2. Term 3, this side is 3. And remember, our x's are the term numbers. So that means actually I can substitute. I can just say, hey, that side is x. That side is x because x is 2. Oh, x is 3. That's x. X is 4. That's x. Great. So I already have part of my equation. It's going to be x times something. So then how can I write the top? What would I have to do with a 1 to make it into a 3? Well, I could either multiply by 3 or add 2. But we already kind of figured out we weren't going to have a multiplier because we got times 1 for the second difference. So it's probably not going to be a multiplier. So I could add 2. I could add 2. 3 plus 2. Ooh, I could add 2. So all of these could be written as x plus 2, right? So if x is 1, that's 1 and a 3. If x is 2, and this is x plus 2, then that's a 2 and a 4. And this is x plus 2, then this side would be 3, and this side would be 5. Yeah, this works. So my top is x plus 2. I mean, the order doesn't really matter, like x and x plus 2. So all I have to do is multiply one side times the other side every time. So the way folks would really write this, they'd write f of x equals x parentheses x plus 2. And remember, I said we're not distributing for now, and there's a reason, because we want this to look like, length times width still. But we should try it out. Let's make sure it works for f of 4. Is f of 4 times 4 plus 2? Like it literally is, right? 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. Yeah, so it literally is 4 times 6, so it's 24. Oh, why did I just do that? I wanted to check and see if my equation worked. It works. So I went kind of fast on all that, I think. And what I told the class was, hey, if you're like, I'm not sure if I'm getting these yet, it's okay. We're going to do more. But I also don't want you to give up. I want you to try to think through the logic. Sometimes if people are having trouble with it, it's understanding that x is always changing and that x is always the term number. And that 1/2 second difference is going to tell you if you're going to have any multiplying involved in the picture. I mean, other than the length times width, but like times 4, times 5 or something. So if you get a 1, then you're not going to have any multiplying. You're going to kind of figure everything out with adding or subtracting. That's sort of the idea. But we'll do more. Don't forget to do the homework that I assigned. Watch the video. And the homework looks like it's a lot, but it's really not. So you'll be fine. And I'll see you Wednesday. Bye. It's better recorded. Seriously, if this didn't record, I'm not doing it again.